Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Essay Introduction. Roy J. Glauber's Quantum Theory of Optical Coherence, published in 2005, represents a monumental contribution to the field of quantum optics. It is a comprehensive and rigorous exposition of his pioneering work, which provided a consistent quantum mechanical description of coherence phenomena in light. This essay undertakes a detailed section-by-section evaluation of Glauber's work, meticulously examining its core arguments, methodological approaches, and the lasting impact of its central claims. The analysis will rigorously assess the validity of Glauber's treatment, its intellectual context, and its significant influence on subsequent research in quantum optics. Section 1: Foundations of Classical Coherence Theory. This section, which lays the groundwork for quantization, introduces the classical theory of optical coherence. Glauber establishes fundamental concepts, including correlation functions and their role in characterizing the statistical properties of light. The evaluation begins with Glauber's assertion that classical coherence theory, while successful in describing many observed phenomena, proves inadequate when dealing with light sources exhibiting non-classical behavior. He claims that a full understanding of optical coherence demands a quantum mechanical treatment. The validity of correlation functions is upheld, which classical coherence theory successfully describes. Glauber posits that there exist fields which are classical in nature, that is, can be described classically, the description of which is significantly simplified via the use of correlation functions. This hypothesis is supported by the observation that correlation functions allow a more complete description of optical phenomena, which provides both the frequency distribution and angular distribution simultaneously. These claims are consistent with theoretical predictions and subsequently confirmed by experimental observations, reinforcing a necessity for a more general, quantum mechanical framework. The conceptual framework is evaluated based on its ability to accurately describe observed phenomena and its consistency with established physical principles. The claim is sound due to its use of a probabilistic approach based on complex field, which naturally describes observed phenomena and predicts future observations. Section 2: Quantum states of the electromagnetic field. Having established the limitations of classical descriptions, Glauber then transitions into a detailed exploration of the quantum states of the electromagnetic field. This section delves into Fock state, number states, and coherent states, with particular emphasis on the properties of coherent states as minimum uncertainty states. The central assertion here is that coherent states, which are eigenstates of the annihilation operator, provide the closest quantum mechanical analog to classical electromagnetic fields. The evidence presented hinges on the mathematical properties of coherent states, demonstrating their ability to maintain their shape under propagation and their generation through classical current sources. This claim receives significant support, notably in its elegance and connection with classical electromagnetism. The methodology relies heavily on operator algebra and the properties of the harmonic oscillator. Evaluating the validity of Glauber's claim regarding coherent states as closest to classical fields reveals a profound insight. They exhibit Poissonian photon statistics, mirroring the behavior of classical waves with fluctuating amplitudes. The conceptual framework is evaluated based on its ability to bridge the gap between classical and quantum descriptions of light, and its ability to describe states with a determinate phase. The introduction of coherent states is consistent with classical electromagnetism and provides a useful tool for investigating the quantum mechanical properties of light. Section 3: The photon detection process. Glauber dedicates a section to the process of photon detection, a crucial aspect for experimentally probing the quantum nature of light. He develops a quantum mechanical theory of photodetection, emphasizing the role of photodetectors in measuring field correlation functions. The claim is that the probability of detecting a photon at a specific time and location is proportional to the normally ordered product of the electric field operators. Glauber presents a detailed derivation of this relationship based on the interaction of the electromagnetic field with the detector material. This claim is strong, supported by both theoretical arguments and experimental verification. The methodology is rooted in quantum electrodynamics and perturbation theory. Its validity rests on its ability to accurately predict the counting statistics of photons, a cornerstone in the experimental validation of quantum optics. The introduction of normally ordered products of field operators allows the definition of quantum fields with classical properties. The theory successfully describes experiments such as the Hanbury-Brown and Twiss experiment, lending significant support to this claim. The conceptual framework is assessed based on its ability to connect theoretical predictions with experimental observations, a critical aspect of its validity. Section 4, First Order, Coherence and Interference. This part focuses on first-order coherence, relating it to the visibility of interference fringes in a two-beam interference experiment, for example, a Michelson interferometer. Here, Glauber argues that the first-order correlation function, one-point correlation function, characterizes the degree of first-order coherence. The observation of high-visibility interference fringes implies a high degree of first-order coherence. The evidence cited includes the mathematical relationship between the visibility and the normalized first-order correlation function. The methodology involves analyzing the superposition of electromagnetic fields and calculating the resulting intensity distribution. The coherence of the two constituent parts of the superposition is investigated. Assessing the validity of this claim reveals its direct connection with Young's double-slit experiment and other interference phenomena. The introduction of normalized correlation functions allows a quantitative comparison among different interference experiments. The conceptual framework successfully connects the theoretical description of coherence with observable interference patterns. This claim is further supported by the fact that the visibility of interference fringes directly relates to the degree of coherence of the light source. This suggests that it provides a connection between a fundamental quantum property and the experimentally observed phenomenon. The validity of the argument is further strengthened through its use for experiments involving both classical and non-classical light sources. The claim also has implications for quantum information processing, where coherent superposition states are essential for quantum computing and communication. Section 5, Second Order, Coherence and Photon Statistics. Glauber then directs attention to second-order coherence, exploring its connection with photon counting statistics and the behavior of light beam splitters. The core argument highlights the second-order correlation function's ability to distinguish between different types of light sources, namely thermal light, coherent light, and squeezed light. The evidence presented involves analyzing the statistical properties of photons emitted by each type of source. Thermal light exhibits bunching, coherent light displays Poissonian statistics, and squeezed light can exhibit anti-bunching. The methodology relies on calculating the second-order correlation function and analyzing its behavior under different experimental conditions. The claim is that these correlations represent a fundamental difference between different types of light. This is upheld due to its ability to reveal non-classical features such as photon anti-bunching, a phenomenon impossible to explain using classical optics. The validity of the section's central claim relies on the successful experimental observation of these distinct statistical properties. The conceptual framework is assessed based on its ability to characterize the statistical properties of light and its implications for quantum optics. The experimental observations of photon anti-bunching provided groundbreaking confirmation of the quantum nature of light. The validity of the claim remains uncontested due to the fact that these concepts have been used in quantum computing and quantum cryptography. Section 6, Coherent State Representation of the Density Operator. This portion of the work focuses on using coherent states to construct a representation of the density operator, specifically the representation. Glauber claims that any quantum state of the electromagnetic field can be expressed as a superposition of coherent states, weighted by a probability distribution P, where the distribution is not necessarily positive. This representation allows one to calculate expectation values of normally ordered operators in a manner that resembles classical statistical averages. The evidence is based on the mathematical completeness of coherent states and the possibility of expressing any density operator in terms of these states. The approach relies on functional analysis and operator algebra. The validity of this section's central claim is more nuanced. The representation does not always exist as a well-behaved probability distribution. For some non-classical states, the function is highly singular, or even more singular than the Dirac delta function. The conceptual framework is evaluated based on its ability to simplify calculations in quantum optics and its connection to classical statistical mechanics. Issues regarding the representation contributed to a deeper understanding of non-classical states of light. Despite these limitations, the representation remains a valuable tool for analyzing quantum optical systems. The representation has implications for quantum metrology, where the ability to measure quantum systems precisely is essential. Section 7, Quantum Noise and its Measurement. Glauber devotes a section to the nature of quantum noise and how to measure it. The central claim is that quantum noise arises from the inherent uncertainty in the electromagnetic field and that its measurement requires careful consideration of the quantum nature of the detection process. Glauber describes techniques for measuring quantum noise, such as balanced homodyne detection, which allows the observation of quadrature squeezing. This section examines the nature of noise, which is the uncertainty in the electric and magnetic field. The methodology involves analyzing the fluctuations in the detected signal and distinguishing them from classical noise sources. The validity centers on his discussion of the inherent uncertainty of quantum mechanics. The section presents techniques for measuring such noise. It is through these techniques that noise can be distinguished from the inherent uncertainty in quantum mechanics. The conceptual framework is assessed based on its ability to explain the fundamental limits on the precision of optical measurements and its applications in quantum communication. The validity is consistently observed in different experiments. This concept in quantum mechanics also has implications for future quantum technologies. Section 8, Applications to Specific Light Sources. In this part, Glauber shifts toward the application of his theory to various light sources, including lasers and thermal sources. He explores the coherence properties of these sources, demonstrating how the quantum theory of optical coherence can explain their observed behavior. The core argument is that different light sources exhibit distinct coherence properties, which are directly related to their underlying quantum statistics. For example, lasers, operating above threshold, approximate coherent states, while thermal sources exhibit chaotic behavior. The evidence involves analyzing the photon statistics and the correlation functions of light emitted by these sources. The methodology relies on applying the theoretical framework developed in earlier sections to specific physical systems. Lasers have coherence properties due to the population inversion between the excited state and unexcited state and the coherence among the photons emitted from excited state atoms. The claim provides a consistent and comprehensive picture of light sources, from lasers to thermal radiation. The conceptual framework is evaluated based on its ability to provide a unified description of diverse optical phenomena, from the highly ordered light of lasers to the incoherent light of thermal sources. This claim is continuously upheld through continued experimental observation. One example is the use of these sources in quantum cryptography, which can be used to secure communications. Section 9, Squeezed States of Light. This section is devoted to the exploration of squeezed states of light, which are quantum states that exhibit reduced noise in one quadrature component of the electromagnetic field at the expense of increased noise in the other. Glauber emphasizes that squeezed states represent a departure from classical behavior and have significant implications for precision measurements. The central claim asserts that squeezed states can enhance the sensitivity of interferometers and other optical instruments, enabling measurements beyond the standard quantum limit. The evidence involves a detailed analysis of the properties of squeezed states and their interaction with optical systems. The approach relies on quantum mechanical calculations and experimental demonstrations of squeezed light generation. The claim represents a significant advancement in precision measurement and quantum information processing. The conceptual framework is evaluated based on its ability to push the boundaries of quantum optics and its applications in diverse fields. The validity of the claim is consistent in different experiments, such as in the LIGO experiment, in which gravitational waves were detected, validating Einstein's theory of general relativity. These uses are further emphasized by quantum computing and quantum cryptography, which rely on precise measurements. Section 10. Atom field interactions and cavity quantum electrodynamics. This part connects the theory of optical coherence with the broader field of quantum optics by exploring atom field interactions and cavity quantum electrodynamics. Glauber describes how the interaction of atoms with quantized electromagnetic fields can lead to novel phenomena, such as Rabi oscillations and spontaneous emission suppression. The central argument focuses on the modification of the electromagnetic field by the presence of atoms, leading to observable changes in the coherence properties of the light. The evidence is derived from theoretical calculations and experimental observations of atom field interactions in cavities. The approach relies on quantum electrodynamics and the Jaynes-Cummings model. The claim serves as a crucial link between quantum optics and atomic physics. The conceptual framework is assessed based on its ability to unify these two fields and provide a deeper understanding of the fundamental interactions between light and matter. The validity of the claim is supported by the successful prediction and observation of various quantum phenomena, such as cavity-induced transparency and entanglement between atoms and photons. This also has implications for quantum technologies. Section 11. Open systems and quantum dissipation. In this part, Glauber considers the influence of the environment on quantum optical systems, addressing the role of open systems and quantum dissipation. This section examines how the interaction of a quantum system with its environment can lead to coherence and loss of quantum information. Glauber claims that these effects must be carefully considered when designing quantum optical experiments and devices. The evidence is based on theoretical models of open quantum systems and experimental observations of decoherence processes. The approach relies on master equations and quantum Langevin equations. This is a crucial concept for the successful design of quantum optical technologies. The conceptual framework is evaluated based on its ability to address the challenges posed by environmental noise and to develop strategies for mitigating its effects. The validity is supported by continuous observation of quantum systems and the phenomena of decoherence. Section 12. Beyond coherent light non-classical effects. This part summarizes and synthesizes the key insights gained throughout the work, emphasizing the unique non-classical effects that can be observed in quantum optical systems. Glauber reiterates that the quantum theory of optical coherence provides a powerful framework for understanding these phenomena, ranging from photon antibunching to squeezed light. The main argument highlights the experimental observations that demonstrate the breakdown of classical descriptions and the necessity of a quantum mechanical treatment. The evidence involves reviewing the experimental evidence presented throughout the work. The approach provides a comprehensive overview of the implications of Glauber's theory and its impact on the field of quantum optics. The conceptual framework is evaluated based on its ability to provide a coherent and unified understanding of quantum optical phenomena. The validity is upheld by continued observation of non-classical phenomena. This claim has implications for quantum technologies, such as quantum computing and quantum cryptography. Conclusion. Roy J. Glauber's quantum theory of optical coherence stands as a pivotal work in the development of modern quantum optics. Its rigorous treatment of coherence phenomena, its emphasis on the quantum nature of light, and its comprehensive framework for analyzing diverse optical systems have had a profound and lasting impact on the field. The detailed, section-by-section evaluation reveals the strength of Glauber's arguments, the validity of his claims, and the enduring significance of his contributions, while some aspects, such as the applicability of the presentation, require careful consideration. The overall framework has withstood the test of time and continues to guide research in quantum optics and related fields. The work represents a triumph of theoretical physics, bridging the gap between classical and quantum descriptions of light and paving the way for revolutionary advancements in quantum technology.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.